In this video, we will complete our work on absolute maximum minima, and at the same time, we will complete our work in this chapter. The remaining sections we do not cover. So I want to do 3 examples. One is purely mathematical, and the other 2 are applications. So the purely mathematical one is exercise 6. It gives you the function f of x of y is equal to x cubed minus 3x y squared and 2y. And it wants us to find the maximum and minimum values of that function on the region bounded by x equal to 0, y equal to 0, and x plus y is equal to 1. Remember, that one can't just ask for the absolute maximum of a function. One must specify what the region is that you want it on. So a quick picture. This describes a triangle. There's our region, say, call it R. So we want to find the maximum and minimum value of this function, taking into consideration all the points inside and on that rectangle. Now recall our procedure. Procedure is to go for the critical points of this function inside the region. Evaluate that function at those critical points inside the region. Then go to each part of the boundary and find the maximum minimum values of the function on that part of the boundary. And so you'd have to do that 3 times, once for each of the sides of the triangle. Then you pick out biggest of all the numbers you've got and the smallest as your absolute max and min. So we'll go for critical points. For critical points, nice function in the point of view that it's got nice derivatives, so we don't have to worry about critical points where the derivatives don't exist. We'll only have to take care of when they're 0. So we'll take f sub x, and that's 3x squared minus 3. We'll put that equal to 0. We'll take the partial with respect to y, which is 2y plus 2, and we'll put that equal to 0, and we'll solve. Nice easy equations to solve. This one tells us that x is equal to plus or minus 1, and this one tells us that y is equal to negative 1. So the critical points are plus or minus 1 and minus 1. Plus or minus 1 and minus 1, since y is negative, then they are not under consideration. They do not lie in R. So not in R. So we don't have to evaluate the function at any critical points inside the region. There aren't any. Which means then the maximum minimum values are going to occur somewhere on the edge. We call this one C1. On C1, that means on here, x is equal to 0. Right? So we'll have f at x equal to 0 and y is equal to, putting in x equal to 0, y squared plus 2y. Call that g of y. We need its critical points. For critical points, actually we should call them critical values because we're in a first-year scenario. The critical value, put 0 equal to g prime of y, which is equal to 2y plus 2, and that equal to 0, and that implies again that y is equal to negative 1. We should perhaps have written here what the values of y that are going to go in. We're on here, so the values of y are between 0 and 1. 0 less than or equal to y, less than or equal to 1. We have this one. Not needed then, he's not in our intervals. We should now go and evaluate, therefore, the function at 0. We take this function and put it in 0, we get 0. Put it in a box. We should evaluate it at 1, and we get 3, put that in a box. So we've now finished on C1. Let's go to C2. On C2, Okay, on C2, y is equal to 0, so put y equal to 0 in our function, f of x and 0, put in y is equal to 0, we get x cubed minus 3x, let's call that h of x. For our critical points on this edge, critical values perhaps, we'll put 0 equal to h prime of x. That's 3x squared minus 3, which implies that x is equal to plus or minus 1. Perhaps we should have put here the values 0 less than or equal to x, less than or equal to 1. So we have 1 that's acceptable. That one. So when we evaluate then h at 1, put in h is equal to 1, we get minus 2 in a box. We should put in h at 0. H at 0 is equal to 0. That's in a box. So 2 down, 1 to go. On C3, the last one, the slanted line on this edge. So on C3, we'll take our function, f of x and y, and we're going to have to express it in terms of one variable. We could go parametric equations for this, but why bother? Why don't we say solve this for y in terms of x and put that into there. So if we do that, we get 3x squared minus 3x, and then we've got plus y squared. So we're going to have 1 minus x, and we're going to square it. And then we've got 2 of 1 minus x. Let's call that one k of x, since there's no y's left. We're going to find critical points of this thing. Values 0 less than or equal x less than or equal to 1. Again, that on here, everywhere along here, x is between 0 and 1. So we're going to go for critical points. Perhaps we could simplify this at first. If we multiply it out, we have 3x squared here and another one there, 4x squared. We have coming out here minus 2x. There's minus 3x. There's minus 2x. That sounds like minus 7x. 2, 5, 7. And then numbers out of here coming a 1 and therefore a 3. So for critical values, we'll put 0 equal to k prime of x. Differentiating 8x minus 7. Oh, I think I made a mistake here. Oh, dear. That's a cubing. So this is a cubed, which means this is a 3 stays as a 3x cubed. And then x's, they should be the same. And the constant should be the same. Okay. So differentiating 9x squared. But there was an x squared in here. All right, so let's do that. We got that. Multiply this out and we get an x squared. Then we had that minus 2x minus the 7x. And we got the 3. Hopefully that's right. Now we've got 2x and we've got negative 7. I don't think that factors. So x is equal to minus 2 plus or minus the square root of b squared 4 minus 4ac. 36 times 4? Right? No, 36. 4ac, 63. 63 times 4. Where is she? All right. 12. And it's going to be a plus sign. 12, 25. All over 18. All right. See if that's what I got written down. I don't have it written down. All right. 256. whatever it is, these are not in 0 less than or equal to x less than or equal to 1. Neither of these numbers is between 0 and 1. But we should go and evaluate then k at 0. If we put it, we get 3. And k at 1, and that gives us 3, 4, 7, 0. So we look at all the boxes and we pick the biggest, and we look at all the boxes and go the smallest. Absolute max. Equals, and the biggest number in the box is 3. And the absolute min, smallest number of all the boxes, appears to be -2. So there's our maxes and there's our min. Clear then how we did it? Again, we go for the critical points inside. There weren't any. If there were, we would have evaluated the function. Then we go to each of the boundaries and we calculate maximum values on the boundaries. And then we pick the biggest of all of them and the smallest. So there then is a purely mathematical example. Now, as I said, I want to do 2 applications of this max-minimum theory. So the first one is to do the following. Find point on the plane x plus 2y, 3z equal 4, closest to the point 7, 8, and 9. Find the point on that plane that is closest to this point. So let's just draw a plane and say, here's the point, 7, 8, 9. Now, I'm going to do this with maximum minimum, but it's not necessary. After we'll finish that, then we'll go back and say there is actually a far easier way. Notice that we do have a formula for distance from a point to a plane, but that isn't really going to be of any use because we're looking for the point that gives that distance, not that distance. So let's set it up as a max-min problem. Call this, if you like, method 1. Just to show that we can get it through maximum minimum, but again, I'm going to do it a different way that is far easier after we've finished. So we'll say, let's do the following. Let's say, suppose x and y and z is any point in the plane, join it to that point. Let's calculate how long this is, and then we will find its minimum value. We'll find out what x and y and z, minimize that distance. Is that reasonable? So that distance is, so if x and y and z is any point in plane, then distance between that point x, y, z and the point 7, 8, 9 is given by d is equal to the square root of x minus 7 squared, y minus 8 squared, and z minus 9 squared. So what we're going to do then is we're going to find the absolute minimum of this function. Now the question is, I said a few moments ago, you can't talk about an absolute max-min problem unless you specify what the values of variables are. So what are the x's and y's and z's under consideration here? And the answer is all of them, right? This plane goes off to in every direction, so x and y and z can be anything they want. So we don't have a minimum problem on a bounded domain like the last example that I did. So we're going to have to do some thinking here in a minute about what to do about that. Because we're supposed to go to the critical points inside the region and then go to the edge, and there is no edge. But we'll deal with that. So objective then is going to be minimize this thing. I propose that we do the following. That instead of minimizing d, let's minimize d squared. Finding the minimum, finding the value of x and y and z that minimizes this is the same as the value of x, y, and z that minimize this. And if I look at this, then I don't have to deal with the square roots. So, all right, let's minimize that guy. Well, one might try the following, but let's see what happens. You might say, all right, let's go differentiate with respect to x and y and z, put it equal to 0 and see what happens. So if you differentiate it with respect to x, you get 2 times x minus 7. If you differentiate it with respect to y, you get 2y minus 8. And if you differentiate it with respect to z, you get 2z minus 9. And if you put those all equal to 0 for a critical point, what do you get? You get x equals 7, y equals 8, and z equals 9. Which is kind of strange because that's this point here. Now it's not strange. The reason it happened is when you wrote down this function, did you take into account at all that the point x, y, z must lie on the plane? You haven't brought the plane in. And so what you're saying here is find the point in space closest to the point 789. And the answer is the point 789. So we weren't ready to differentiate. Another way to see it is here that x and y and z are not independent variables. So you shouldn't be differentiating it yet. So that's why that didn't work. So we need to put in here, get independent variables. That means either replace x's with y's and z's, or replace y's with x's and z's, or replace z with x's and y's. So you go back to the plane here and say, which one would you like to solve for? Well, it's not hard to solve for any of them, but if I solve for x, I'll at least avoid fractions. So let's solve this for x and put it into here. So we will have then 4 minus 2y minus 3z minus that 7 squared, and then the other 2. So there's the function that we want to minimize now. And y and z are independent variables, and y and z can be anything they want. In other words, what we're doing is minimizing this function, taking into account everybody in the yz plane. So let's go get our critical points. For critical points, we will look at 0 equal to d squared y, and 0 is equal to the derivative with respect to z. So if we differentiate with respect to y, bring down the 2. Why don't we simplify this thing here before? So if I take that and that, then that's a minus 3. How do we throw away all the negative signs? Because it's squared anyway. And write plus 8, plus 8, plus 8. You don't have to do that. You'll get the same thing if you don't. So if I do that, I brought down the 2. I lower the power of 2y plus 3z plus 3. And then I go inside differentiate with respect to y on 2. So there's the derivative of that with respect to y. The derivative of this, 2y minus 8. And the derivative of this, 0. Repeating with z. Bring down the power. lower the power by 1 and go inside, and then differentiate the other one, 2z minus 9. So what you now have are two equations. In fact, they are linear equations to solve for y and z, which I'm not going to do. I hopefully have the answer written down. So when you solve these two equations, you get that y is equal to, and z is equal to. Y is equal to 26 over 7. Z is equal to minus 6 over 7. And if you put those back into the equation of the plane, put that y here, put that z here, solve for x, you get that x is equal to 26 over 7. So here's our critical point, right? So critical point is, and we have only one, 26 over 7, 26 over 7, and minus 6 over 7. All right? Now again, our procedure. We're trying to minimize this function, taking into account everybody in the YZ plane. So what we normally now do is go to the edge, but there is no edge. So what are we going to say? Well, let's just think about it. You're trying to find the point in this plane closest to that guy. You found one and only one critical point. No more. And if you start saying, if I start letting x's and y's and z's, or y's and z's get big, the distance is going to get huge. So doesn't this point have to be the point that we want? It has to be the one that's closest. There's no other place it could be. So this is the one that we want. So this one is the closest point. Right, so we've gone outside of our theory where we had a maximum problem on a closed bounded region. That's not happening here, but we've reasoned our way through it. That was method 1. Method 2. Much easier, and it draws upon the fact of what we did in chapter 11. Method 2. Consider the following idea. We know, do we not, that the closest point here will be when that line is perpendicular to the plane. The closest and the perpendicular distance are the same. So why don't we do the following? Why don't we find equations for that line? Because we have this point on it, 7, 8, 9. And we know it's perpendicular to the plane. So a vector along would be 1, 2, and 3. So let's find parametric equation for the line. So let's call this, that one, all right? So let's call this one P, and let's call this one Q, right? So parametric. For line PQ from P, perpendicular to plane, R, x equal, y equal, z equal. X equal 7, y 8, 9. T, T, T. In front of the T, put the 1, the 2, and the 3. 1, 2, and a 3. Those are parametric equations for that line. What do we want? We want where that line intersects this plane. We want the intersection point of that line and that plane. So all we have to do is put these ones together. So why don't we take this and this and this and put it into here, here, and here, and solve for t. Get that t, put it back here, and we'll have the point we want. Right? So, we say then 4 foot of perpendicular in plane. We'll do the following. We must you can see, put that and that and that into there. So we'll have 7 plus t. We will have 2 times 8 plus 2t. Then we'll have 3 times 9 plus 3t equal to 4. So we need to solve this for t. So if we solve, let's see, t, there's not 4 more, that's 5t and 5t and 9t. 5t and 9t, 14t equal to 7 and 8 and 16 are 23. 23 and 27, 60. Take that over to the other side, 60 minus 56. T then equal to, that's minus 4? Minus 4. Can't be, that's not the right thing. 14p, 46. 46. Apparently that number is wrong. 7 and 16 make 23. 23 and 27. 23 and 27. That's 50. Oh. That comes over, this is minus 46. Oh. So minus then 46 over 14, which is minus 23 over 7. How does that look? Is that what I got written down? Yes, all right. All right. So if you take that and you put it back into here and into here and into here, gives you x equal what we had before, 26 over 7. Y was equal to, I've forgotten, x was equal to 26, y was equal to 10. I think I wrote down the wrong one before because I know I got this. Y is equal to 10 over 7, and z is equal to minus 6 over 7. I believe I wrote down this one wrong before. Seems I had 2 26s and a 10, so correct that. All right, let me check again. X is 26 over 7, y is 10 over 7, and z is minus 6 over 7. I guess that doesn't, right? All right, and that should be the same point that we had before. You can see definitely this is a lot easier procedure using what we had in chapter 11. So there's an application of max-min, but it can be done by a better method. Second one that's an application is one of the exercises. Exercise number 20. Exercise 20. I'll describe it to you. What it says is the following. You're given the ellipsoid x squared over a squared, y squared over b squared, z squared over c squared is equal to 1. If a, b, and c are equal to 1, then you've got yourself a sphere. So this is an oval kind of shape. I'll draw what's in the first octet. So looking like this. So this is A, and this is B, and this is C. And there are 7 more pieces just like it, 3 more on top and 4 underneath the x1 line. And it says what you're supposed to do is draw boxes inside this ellipsoid with sides parallel to the x and the y and the z axes. And you're supposed to find the one that's got the largest volume. Find the biggest box that you can put inside this ellipsoid with sides parallel to the axes with biggest possible volume. That's your problem. The problems of this nature, the hardest thing is to get it set up. The rest of it, after you set it up, is mechanical, do the differentiations and so on and so on. I would suggest we do the following. Let x and y and z be a point on the ellipsoid. do you agree you're going to want to extend the box out to and touch the ellipsoid? If you take one that's inside and doesn't go touch the outside, or touch the outside, then you can make it bigger. So I suggest that we take a point here on this first octant part of the ellipsoid and construct out of that a box and say, all right, the box is going to come down and it's going to go back over there and it's going to go up. Right? No, that's down now. It's going to go this way. Right? Right? All right. So draw this box, right? So that, right? And it's going to go back that way, and down as well. Can you visualize that box then coming from this point? Take it here, draw it back to over there. Take it here, draw it back over here. Take it here, draw it back down to there, right? And then finish the box. So I show really here only 1/8 of it, right? That's 1/8 of the full box. So we want to maximize the volume of the full box. What's the volume of the full box? Well, would it not be then 2x times 2y times 2z? 2x for this dimension, 2y for that dimension, and 2z for that dimension there. So 8xyz. So there's the function that we have to maximize, but like in the previous problem, x and y and z are not independent. We haven't yet demanded that this point has to lie on the ellipsoid. So that means replace one of these guys with the other two. So let's replace the z. We solve this for z. Over with u, take square roots and up with the c. Square root 1 minus x squared over a squared minus y squared over b squared. And let's put that into there. So we'll have volume is equal to then 8cxy square root of 1 minus x squared over a squared minus y squared over b squared. There's the function then that we've got to maximize for the largest possible box volume. Absolute max problem. What's the interval? What's the region? We're talking about the x's and y's here. Where can the x's and y's be? Where are all the x's and y's that we're going to look at? That's your next hurdle. So think about it then. Right? We want to take into consideration, basically we want to say, we want all the points that are on this part of the oval. So what values would x and y would choose? I think it would be these people. All the values of x and y in there. If you take any x and y in here, it gives rise to a point on the ellipsoid. So the region, this is our R region. Could we say R is x squared over a squared plus y squared over b squared less than or equal to 1. That, with an equal, is the equation of that ellipse. So that's the region. Maximize this function, that region. Right? Which means we're going to go for critical points inside the region, and then we're going to go to the edge and talk about the edge. And there's 3 parts to the edge. Here, here, and here. We'll get to that later. It turns out to be quite simple. So for critical points, we will set 0 equal to di v di x. So we have to differentiate this with respect to x. I guess that's going to mean a product. So we will have 8cy, the square root, 1 minus x squared over a squared, y squared over b squared. So that's that one times the derivative of that one. Then we're going to need this one times the derivative of that one, plus 8cxy, differentiate the square root, bring down the 2. Lower power, which means the square root is going into the denominator. And then differentiate what's inside, minus 2x over a squared. How does that look then for the derivative of the square root? Write down the power, lower the power by 1, went inside. And a similar one for y, differentiate respect to y. Product rule again, 8cx, the square root, 1. Plus 8cxy, and now differentiating the square root with respect to y. Bring down the power. Lower the power by 1. Go inside, minus 2y over b squared. So these are the equations that we're going to have to solve for critical points. Ugly. Let's simplify them a little bit. Let's throw away the 8c's, just so they don't look quite so bad. Let's cancel that 2 with that 2, that 2 with that 2. Didn't help a lot, but here's what I would suggest if I were going to solve these equations. What I would do is I would bring these 2 to the square root denominator. I would take these 2 and get this denominator underneath. So let's do that. So if I do that, and then, right, so I'm going to do that, I'm going to take this one and multiply it by here and put them both over here, and then I'm going to throw the denominator away because I need it equal to 0, so the numerator must be. So I think I'm going to have that y times 1 minus x squared minus over a squared minus y squared over b squared. Because that's that square root times this square root. Then plus this one here. So minus x squared y over a squared equal to 0. So how does that work? Got the x squared, and it's a minus sign. All right. Do the same thing with this one. We will have x times 1 minus x squared over a squared minus y squared over b squared. And then this time we will have minus y squared x over b squared, likely. Y squared x, all right. Now they're looking better. Now they're looking better. Solving now. Here's what I would suggest. That we multiply this one by x, we multiply this equation by y, and we subtract, and that will kill all of that stuff right there. All right? So doing that then, multiplying this one by x, what will be left is minus x cubed y over a squared, multiplying this one by y, and then subtracting, plus xy cubed over b squared is equal to 0. Let's take these and factor out an xy. From here then we would have a y squared over a b squared, and for this one minus an x squared over an a squared is equal to 0. Things are looking better now. We have a choice then of putting x equal to 0, y equal to 0, or this equal to 0. But x equal to 0, x equal to 0 is actually this edge, which we're going to get around to anyway later. And y equal to 0 is this edge, and we have to get around to him later. Sorry, those guys are not putting the critical points inside, they're critical points on the edge, and we're going to take care of the edge later. So therefore, let's just look at this one. I don't want to rub too much off. I take one of these off, it should be all right. So it means then, this one is telling us then that y squared over b squared is equal to x squared over a squared. Or y is equal to plus or minus bx over a. Now we don't need the plus or minus because the x's are going to be positive, the x's are in here. And if you chose the minus, then the y would be back there, and we don't want that. So we don't need the plus or minus. So y then is going to be bx over a. All right. So now where? We need to go get the x. We could take any of the equations that we want. You don't take this one, because that's where we got that guy from. We could take that one, or we could take this one, or we could take this one, and put in, and see what happens. So let's put it into here, right? So let's put that into there, and see what we get. So we will have y for out there, bx over a, 1 minus x squared over a squared, then y squared over b squared, that was this thing, and a minus then, minus x squared over a squared, and then minus x squared over a squared times the y, which is bx over a, is equal to 0. So we've got that thing to look at then. Well, notice we could cancel that with that. Again, what you're really saying is, but x could be 0, but we know we're going to take care of x equal to 0 later, so we've lost nothing. So what do we now got? Oh, 1 minus, they're all the same, 3x squared over a squared equal to 0. So x then is plus or minus a over root 3. And again, we don't need the plus or minus because ax has to be positive. So x is positive. There's an x there. That implies that y was equal to this, b over a times the x, a over root 3. So that's b over root 3. And you'll also, if you put that back into my ellipsoid equation, which I erased, you're going to get z is equal to, not to be unexpected, that. So there then are the x and the y and the z. We don't need to put z quite yet. We've got to consider that we've got this one and only one critical point. We've got the critical point a over root 3 and b over root 3. For that volume function that we were looking for, the maximum of. One critical point. Somewhere here, a over root 3 and b over root 3, there it is. We should go and evaluate the volume function at that guy and put that number in a box. All right? I'm not going to do that. Right? But I should. And then I should be going to the boundary. So let's go to the boundary. Unfortunately, remember what my volume function was? It was 8c xy square root of 1 minus x squared over a squared minus y squared over b squared. That was the volume guy after we substituted for z. So we're supposed to go to this edge. But along this edge, y is equal to 0, and you put that into here, and you get 0 volume. You're supposed to go to this edge. That's where x is equal to 0, you put x equal to 0, 0 volume. You're supposed to go to this edge, which has this equation, right? If you make that into an equation, and you put that into here, that's 0. So every point on the edge gives a volume of 0. Does it not follow then this guy has to give the maximum volume? There's no other place it could be. So going to the edge here is trivial, right? So, right, so if I have a question said, what are the dimensions? Remember, the dimensions are 2 x's, 2 y's, and 2 z's. So the dimensions are going to be 2a over root 3, 2b over root 3, and 2c over root 3. Those are the dimensions of the box that's going to maximize that log inside the ellipsoid. All right? So that again completes everything that we're doing in chapter 12. There's a couple more sections there, but you're not responsible for that material. Next time, we'll start talking about double and triple integrals.